A theory published earlier this year claims our understanding of gravity that was first proposed by Einstein could be completely wrong. Now for the first time, this controversial theory has been tested experimentally and has held its ground. An independent study of the distribution of gravity around more than 30,000 galaxies found evidence to back the theory, and if confirmed, it could rewrite physics entirely. Professor Vernon from the University of Amsterdam published the Vernon's hypothesis of gravity earlier this year. The paper was an attempt to solve the mystery of dark matter. When studying stars and galaxies, astronomers have found the forces of gravity appear stronger than expected. The outer regions of galaxies, like our own Milky Way, rotate much faster around the center than can be accounted for by the quantity of ordinary matter like stars, planets, and interstellar gases. Traditionally, physicists have explained this inconsistency by assuming there must be something else out there we cannot see called dark matter. Dark matter particles have never been observed, despite many efforts to detect them, and astronomers currently infer their presence through observing certain gravitational effects on the matter we can see. Professor Vernon says we need to rethink gravity, removing dark matter from the equation completely. To do so, his controversial theory suggests gravity is not a fundamental force of nature at all, but rather an emergent phenomenon. Professor Vernon's theory started out as a paper published in 2010 and it had remained untested until now. A research team from Leiden University in the Netherlands has finally tested it, providing the first experimental evidence the controversial hypothesis could be true. The team, led by astronomer Marco Brouwer from Leiden Observatory, looked closely at the distribution of matter in more than 30,000 galaxies. They found the distribution of the matter could be explained without dark matter when using Vernon's hypothesis of gravity. The researchers used gravitational lensing, a visual effect in which the galaxies closer to Earth bend the light emitting from more distant ones, a well-established way of measuring a galaxy's mass. The gravity of galaxies bends space, such that the light traveling through this space is bent. This bending of light allows astronomers to measure the distribution of gravity around galaxies, even up to distances 100 times larger than the galaxy itself. The team made predictions about the galaxies using both Einstein's classic theory of relativity and Vernon's hypothesis of gravity. They then compared the two by seeing how these predictions matched up with their observations. They found while both theories of gravity made correct predictions about the galaxies, Vernon's hypothesis did so without using any free parameters. Free parameters are values that can be tweaked, essentially cheat values, to ensure that observations about a galaxy match an initial hypothesis. The researchers measuring the galaxies said factoring dark energy into their equations meant they had to use 4 of these free parameters. The dark matter model actually fits slightly better with the data than Vernon's prediction. Lead author and PhD student Marco Brouwer told New Scientist that then if you mathematically factor in the fact that Vernon's prediction doesn't have any free parameters, whereas the dark matter prediction does, then you find Vernon's model is actually performing slightly better. If the theory passes more tests, it could dethrone over 100 years of physics and even throw out the theory of dark matter altogether. If eventually proven true, Professor Vernon's hypothesis could lead us to a theory of everything which combines the observable world of classic physics with the elusive world quantum mechanics. The question now is how the theory develops and how it can be further tested, said Mrs. Brouwer. But the result of this first test definitely looks interesting. Describing his theory last month, Professor Vernon told Dutch news site NOS, "Our current ideas about space, time, and gravity urgently need to be rethought. We have long known that Einstein's theory of gravity cannot work with quantum mechanics. Our findings are drastically changing, and I think that we are on the eve of a scientific revolution." The new theory, called emergent gravity, suggests gravity comes as a side effect of the entropy of the universe. Entropy describes the amount of disorder in a system. Professor Vernon took the entropy of the universe and used it to adapt a theory called the Holographic Principle by Gerard T. Hooft. He says gravity emerges from the changes of fundamental bits of information stored in the structure of space-time. At large scales, it seems, gravity just does not behave the way Einstein's theory predicts, he said. He says dark energy, the mysterious force causing unusual things to happen in the universe, could be to blame for the increased gravity in stars and galaxies. In that paper he showed how Newton's famous second law, which describes how apples fall from trees and satellites stay in orbit, can be derived from underlying microscopic building blocks. He has since demonstrated that when you factor this new definition of gravity, it no longer needs a new particle to account for dark matter. The behavior of galaxies makes sense without it. We have evidence that this new view of gravity actually agrees with the observations, Professor Vernon said. At large scales, it seems, gravity just doesn't behave the way Einstein's theory predicts. Dark matter is not the only theory that does not fit in with our current theory of gravity. The Standard Model says everything in the universe is made from the most basic building blocks called fundamental particles that are governed by 4 forces: gravity, electromagnetic, weak nuclear, and strong nuclear. But the Standard Model has left some questions unanswered for years, so scientists scientists are keen to break free of it and find new theories. It can't explain gravity, for example, because it is incompatible with our best explanation of how gravity works. General relativity, the quantum theory used to describe the small particles in the world, and the general theory of relativity used to describe the larger objects world, are also difficult to reconcile.